Hi guys, we're beginning now in 1 minute. Hi guys, we're beginning now. Never mind. In 1 minute. Okay, basically these are the different topics that we have to discuss. Uh, Here they are. Okay, so what we're going to discuss: basic pre-calculus review, like using that becomes more interesting stuff. Um, the topics there are the volume of a solid using the different methods like the disk method, shell method, washer method. Two of those questions on the test that I have to take tomorrow. One integration by parts, one trig sub. Actually, I might have misheard. It might actually just be a normal trigonometric integral. Not sure. So we'll review both. And then given an improper integral, determine if it diverges or converges. And then obviously if it converges, you find the value. So that's easy enough. Besides that, there are few integral test ones. There's a few different test ones. There's one integral test, limit comparison test. This one you pick any test and then use it of that series question. So anyway, we've done enough of that. Now let's actually begin. First topic is just using a line. Somehow the screen went into Russian automatically. Not sure how that happened. So we'll move on without that. We'll go on without that. First one is just the equation of a line. This is very easy. That shouldn't really be taking time on this. Let's say we're given like the point 3. I'll just thicken the pen a bit. 1 second. Yeah, like let's say you're given the point 3, 3, 3 comma 3. It's still too small. And you have to you're also given I don't know what was shown and what wasn't, because this is very slow. I don't know, so I'll just go back from the top here. Let's check. Okay, basically the point is 3, 3, m equals 4, so y equals mx plus b. That's a formula. Y is equal to 4x plus b by plugging in m equals 4. Plugging in the point, we get 3 equals 12 plus b, which means b equals -9. And we can plug this back in to this equation to give us y equals 4x minus 9. Right, that's basically how you do it. Obviously, questions can get harder, but all of them will have the same general idea. So nothing will, that's really all there is here. So such an easy unit, so we're done already. Next one is area between two curves. I tried to read it. So yeah, basically just the area between two curves. And the formula over here, it's written over here. It's f of x minus g of x. Integrate that from a to b. And just to show you what that means, kind of just to review that. Let's say this is the y-axis, this is the x-axis. Let's say this function here is y equals g of x. And then we'll say this function over here, this here is y is equal to f of x. If you want to find the area between, and let's make it like this. So if you want to find the area between these two, what are you finding? You're basically finding this area, right? Like this black colored in area. And to find that, think about it. What is the height over here? Like what is this height? What is this height? You want to add them all up, right? And the height here is obviously just f of x minus g of x. So the height is f of x minus g of x. Let's call this point a, right? X equals a. This point x equals b. And then we have it right here, the integral from a to b of f of x minus g of x. And obviously you have to add the dx as well. That's kind of where it comes from, the formula. Now let's use that to do a few of these questions here. I'm not going to do all of them because there's 7 questions. I don't want to take too much time on that. But we can do 18. That's like a good representative question. Let's zoom all the way in here. Now notice that in the other ones we're given bounds. We're given x equals 0, x equals 1. Over here we don't. But we can I cut that part out. But the question basically said to find the area between the two curves. Um, and to find that, we can just figure out the endpoints ourselves. To do that, we can just equate the two. So negative x squared plus 3x plus 1 equals negative x plus 1. To solve this, it's actually very easy. Just these cancel out automatically. We get 4x is equal to x squared. So x is equal to 0 or 4. Those are our bounds. So we have 0 to 4. Which is a bigger function over here? That's the next thing we need to figure out. If we can plug in any value between these two. So we can plug in 1, let's say 1. Over here, you can see the first equation here becomes negative 1 plus 3 plus 1, which is obviously more than negative 1 plus 1. So our answer will be this is the bigger one. This one is bigger. And so we can go ahead and write that in. So it's going to be negative x squared plus 3x plus 1 minus the other one. So it'll be minus negative x, so plus x, and then minus 1. Um, yeah, and then there's a dx here. Let's just cancel some stuff. The negative 1 cancel out. We're left with integral from 0 to 4 of negative x squared plus 4x dx. How do we figure this out? Let's move over to the right over here. This becomes negative x cubed over 3 plus 2x squared. And then we just put the bounds 4 and 0. With 0, it'll all be 0. So it's basically just evaluating this at x equals 4. Negative 64 over 3 plus, 32, right? Plus 32, which we can simplify to 32 over 3. So we'll write that over here. And that's a good question. Let's see if there's a harder one here. Yeah, last one seems good as well. 21. So let's x to the 5th plus 1 and x to the 5th plus 2 and x plus 2. So again, we solved them. This one we can do mentally. If you just equate them, you get x to the 5th equals x, or x to the 4th equals 1, which means x is equal to 0 or 1. Or actually, negative 1 also works there, right? Negative 1 will also work. So we've got negative 1, 0, and 1. Let me just check that once. So obviously 0 works, 1 works, and then, yeah, all three work. Those are the only points of intersection. Let's see how to do that then. First thing to keep in mind, we don't want to actually graph it, but if you think about it, um, we will graph it. 1 second. So this is the y-axis. This is the x-axis. Let's just like roughly sketch them out and see uh, how we want to, like, do we need one integral? Do we need two integrals, etc. At 0, both of them are going to be at 2, right? At 1, they're both going to be at 3. So it'll be like right there, 1 comma 3. There's a difference in how the functions go there. One is just going to be a straight line, right? One is going to be a straight line that literally just goes like this. The other function, on the other hand, is going to be, so this is g of x, right? This is y equals g of x. And I'll just mark these points here so you can see these are the intersection points. With f of x, it's going more like this. And then over here, it'll again go like this. Okay, so this function here is y equals f of x. You can see in this interval, it's okay, it is hard to see, but over here, f of x is greater than g of x. So f of x is greater than g of x. And it's the other way over here. So and we can prove this pretty easily. You can literally just plug in any value in between and do it, but it's easier to just see it with the graph. So I'm not going to actually do that. Here we just have f of x minus g of x dx. And then we add, so this is that area over here. And the other area over here is from 0 to 1. It's going to be g of x minus f of x. Okay, g of x minus f of x. So all that's left to do now is evaluate these two, which we can do pretty easily. The nice thing is that f of x minus g of x and the other one, when you subtract them, the 2's will cancel out. So this just becomes essentially, 1 second, something is cutting my foot. Some splinter or something, whatever it is. Okay. So this one will just become x to the fifth minus x. You integrate that from -1 to 0 dx. I'm not putting the brackets just to save time. And then here we have from 0 to 1 x minus x to the fifth dx. When you integrate this, you get x to the sixth over 6 minus x squared over 2 from -1 to 0 plus x squared over 2 minus x to the sixth over 6 from 0 to 1. This one is easier to evaluate. We'll do that first. It gives us half minus 1/6, which is 1/3. So this is 1/3. Yeah, that's 1/3. Over here, 0 is nothing. And actually, yeah, this has to be the same thing as this. Okay, so this will basically become this will basically become 0 minus uh 1/6 minus 1/2. But -1/6 minus 1/2 is 1/2 minus 1/6. I'll write it out actually. Okay. So this is what we have. 0 doesn't matter, so it's this, which becomes 1/2 minus 1/6, which is also 1/3. So they're both the same. One more way to do it is that both of these are odd functions. Wait, no, they're not. Never mind, never mind. Anyway, 1/3 plus 1/3. So you add them up, and that gives you 2/3. So for this question over here, 2/3. Okay, now that's enough of this concept. Right. Oh wait, let me check if there are any messages in the chat. No. Okay. That's basically all there is for this concept. So it's pretty easy. We could also do it around the y-axis, but it's literally the same thing. You just change up the dy to a dx. This is a lot more interesting. This is it's something I can't really read it. So um, basically, it's a disk method, washer method, and shell method. This is the washer method. In the middle, the top one is a disk method, bottom is a shell method. Let's do one of each, like a basic example of each, then we'll move on to the questions. So we'll begin with the disk method. Wait, let's see. Yeah, the spellings differ. Like that one's with the K, this is the C, but I think this is the Indian way, so I'll put it like this. And yeah, basically, this is just to rotate it about some axis. We'll take the x-axis. Okay. So let's say our function is can be anything, but let's say it's x squared. So it's like this. And now we want to rotate it about this axis. Okay, so if you want to imagine that, it's basically like this, and then you rotate it. So it'll be um like this, except it's 3D. Okay, just try to imagine that. So 1 second, sorry. Like this. Okay, that's basically what it'll look like. We want to find the volume of that. Remember, it's 3D, so we need to find the volume, right? That's a bit harder to do. So, let's see how we can go about doing this. Uh, you can, the point of the disk method is to basically imagine circles. Like this is one, let's zoom in a bit. This, we use this height over here. The height is, let's actually just call this y equals f of x. Let's begin with that. That's obviously the thing to do. So this height here is obviously going to be f of x, right? This is uh f of x. Yeah. To find the volume, think about it as just like one circle here, another circle here, another circle here, another circle here, another circle here. You keep on adding up their areas. Obviously, you're not going to add them up. You integrate them. Um, and then once you have that, you get the volume. So to do that, think about it. F of x is the radius, right? What's the area of a circle? Pi r squared. So it's pi f squared. No, not f squared. I think that represents a composite function or something. So I'll just write f of x squared. Right? That's what we have. Now what we do? We integrate it from a. Over here it looks like 0, but just treat it as a until b. So we integrate this from a to b. And then obviously we add a dx there. Okay. Now pi is a constant, so we can just take that out. Then we have a to b. Instead of f of x, if you call it r of x, you get r of x squared dx. And that's the disk method. So now all that you have to do, literally just use the formula, right? Let's say, actually, let's make it interesting. Okay, let's begin with y equals y equals x squared from x equals 0 to x equals 1 to 3. Okay, x equals 0 to x equals 3. And we want to find the volume. So it's going to be pi, 0 and 3 are our bounds. So 0, 3, x squared squared dx. This is literally all we do. We get this, right? So just squaring it, obviously, that stays 3. This becomes x to the 4th dx, which is x to the 5th over 5. There's a pi in front. 3 and 0, which becomes 243 pi over 5. Okay, the reason I chose 3 was it was my mistake. I should have chosen 5, or I should have made this just x, because I wanted to make it a nice neat number. Instead, let's do the same thing with y equals x from x equals 0 to 3. Okay, just very quickly so you can see. And there'll be something interesting at the end of this question. So it's x, you square it, then you multiply by dx. This becomes x squared 30 pi dx. And this becomes x cubed over 3. There's a pi in front, so I'll just sneak it in over there. 3 is over there, 0 is over there. And this becomes 27 over 3, which is 9 pi. Okay, we've got the answer. But now note that since this is x, it's just a straight line, right? Let's quickly draw it out here. Y equals x, that's this over here. This is the y-axis, this is the x-axis. And we're rotating it from 0 to 3. Okay, and we want to find the volume. If you rotate it, this is just going to be a cone, right? And when you do that to a cone, well, think about it. If this is 3, then obviously this is going to be the point 3, 3, right? Since it's y equals x. Which means, now when we, okay, let's take this into the next dimension. Let's take this into the third dimension. We'll have something like this. Okay, I'm going to try to make it easy to see. Okay, it looks odd, but this is basically f of x. So this here, or r of x, I'll use r of x from now. One second, let me redraw the cone here. Yeah, it looks ugly now, but just bear with me. This is r of x. This is h of x. But in this context, h of x is literally just um, x, right? From 0 to x. Over here, x is 3. X is 3, so this is just 3. Similarly, r of x, the way we've defined it, we've gone from 0 until 3. So this is also just 3. So now we've got a cone with height 3 and radius 3. Volume of a cone is pi, wait, I forgot. Um, pi r squared h over 3. Yeah, pi r squared h over 3. And when you plug in the same values here, it's pi times 3 squared times 3 over 3, which becomes 9 pi. So same exact thing here. So it does hold. Like if you didn't believe me until now hopefully this will help you believe it a bit more. So it does work. That's basically the disk method. Then there's the washer method. And I'll just use the same diagram over here to do that. This is very similar to the area under the curve, by the way. So let's say here we've got something like x, like right there. Okay, let's say this is y equals g of x. And we'll do some examples so that you can get more information about it. But now we want to rotate the area between them. So we want to rotate this area around the same axis. Everything is the same. We're just rotating this area instead of this entire area. Okay, that's basically what we're changing here. Okay, so this is a bit harder to do, but we can actually use what we did in the last question, except use it twice. This area, if you rotate it around, there should be a picture of it in this book. One second. Should be a good picture somewhere. I'll try to find it. I don't know if I can. So actually, let it be. I think you'll understand anyway. Um, this is our function, right? What if we take the volume of this entire thing? So what if we take f of x squared dx from whatever a to b? So that gives us the whole volume. And then to get this part shaded in, what if we just remove this volume? That will be the same thing, right? Like now if we do this, That's the same thing. Okay, so it's like in math questions when you're asked to find, let me give you a very quick example. Like over here, when they ask you to find this area, you can't directly find that area. So instead you find this big area and then you subtract this small area, which leaves you that. That's how you go about doing those questions, and it's the same over here. So we can just use this. Now we've got the same bounds and everything. We've also got a pi, so we can just take the pi out. We get this a to b, um, and we can move these all under one, make them all one integrand. Okay, so it becomes f of x squared minus g of x squared. Wait, I should have put this, whatever, g of x squared, all d, and then dx. Okay, now this makes sense, and we understand that, but before doing that, this is something that I did when I first tried to do this. I tried to just do this. Okay, this is f of x minus g of x, right? This is f of x minus g of x. What if you rotate this instead? Like, what if you just do this, right? You can rotate this about it, like make this a new function essentially. So you just do the integral from a to b pi of f of x minus g of x, and then you still have to square it because that's a new function. So that becomes your r of x. You still have to square it dx. This is what I used to think, and it's wrong. Now I'm not sure why it's wrong, but it is wrong. I can't really explain why. There's probably a pretty obvious reason for it, but yeah, it's like kind of like y x cubed minus 1 isn't the same thing as x minus 1 cube, right? That similar to that, like you can't do this. It's um if you rotate just this shape around, you'll end up getting something different. You won't get exactly that because it'll be, yeah, you, instead of getting a curved surface, you'll just have like a straight, when you rotate it, you'll just have like a whatever. Well, I ignore whatever I just said. Basically, it's not this. So don't get tricked into thinking that. It's like this. You square f of x, you square g of x, you subtract them, and then you integrate. That's basically how you do it. Let's do now that we run disk and washer methods. This is the washer method. Right? Now that we've done both of these, let's do a nice practice question. This is shell method. This is also shell method. Yeah, these two are nice questions. Oh, there's also this one over here actually. So let's do this actually. Nice question. By the way, all this stuff is from Calculus Early Transcendentals. These are where the questions and everything are coming from. By I forgot the author's names, but it's got a nice cover. Anyway, basically use a graph to match the integral, right? So let's start. I didn't mention some stuff. I didn't mention that when you rotate it about the y-axis, like when you rotate it like this, then you do dy basically. As far as we know, like from the disk and washer methods, you do dy. So so that already gives us a hint. When you're rotating it about the y-axis or x equals a, which is a vertical line, then you'll end up having dy and dy. So we know that. Um, and then obviously it's the other way around with x. If you're rotating it about a horizontal line like the x-axis or y equals b, you'll have dx or dx. So let's do it now. The first and easiest one is just this, right? F of x. If you're just doing this, you're squaring it and then you're multiplying by pi. That's literally just a definition of the washer method, right? Where a is 0 and b is a over here. Basically, same exact thing. So obviously this matches with this. These two match. That means that the only other horizontal line will match with the only other dx. So it's like this. um there's another way to figure this out. It's basically you're rotating it about the b axis, right? You want to find this area, so you do this big function, so b squared minus, and then you try to find hi uncle, then you try to like subtract all of this stuff, and each of these heights over here is just going to be b minus f of x. So you subtract that, and That's the person in the chat right now is one of my big fans, Ankur Banerjee. Sorry, Ankur. Um, he's also very passionate about calculus and math in general. Yeah, so basically this becomes b minus f of x. Very messy over there, but basically it becomes this. Now we have to look at something a bit more complicated, right? We can see with the y-axis, we've got the y-axis and the line x equals a. With the y-axis, we want to find this area, right? How can we find that? Well, it's going to be a minus um, minus f of x, right? That's going to be this over here. And we keep on integrating that. From where to where though? We go from 0 to b, because when we're rotating it with respect to y, and the y coordinates here are, this is 0 and this is b. It's written over there. Okay, so that's out of the way. How do we do this though? Well, one of them will be, let's do y equals, x equals a. That's actually easier to do, even though it might seem the other way around. And let me clear some space over here. I've taken up too much there. Okay, let's do it now. When you're rotating it about this, remember this is still b, this is still 0. So you still integrate from 0 to b. And there's obviously still a pi in front. What you put in here though is just this height over here. And it's just classic, classic disk method there. So it's this height. How do we represent that? That's going to be, um, okay, x is f of y. They've given that to us. So it's going to be f of y, right? And that's the height over here is not f of y gives you this height, right? That's f of y. So you just do a minus f of y, which will give you this length over here. And then you keep on integrating that. But to integrate it, this is basically your r of y. So you put in r of y and you square it. So a minus f of y squared dy. So this one right here matches with this equation here. With the y-axis, it's a bit more complicated because you have to subtract off. 1 second, wait. Yeah, because over there you have to subtract off the volume of this entire thing, right? You find that volume and then you subtract this volume, which is exactly what's written there. That's just a basic application of the washer method. So that's a matching scheme or whatever you want to call it. That's the answer for this. Okay. Now that we're done with that, I was trying to make it a conceptual thing so that it would be easy to understand, but I realized I made it trickier and less fun. Oh, wait, actually, never mind. I kind of messed up. This is shell method. This is also shell method. And this is also shell method. So I think we've done enough practice with the disk and washer methods. Let's move on to the big dog here, which is the shell method. So it's already looking a bit complicated, but it's actually very useful. Okay, let's take a look here. So if you're rotating it about I'll do this one first, vertical axis, because I use it for that more. When you're rotating it about the y-axis and it's hard to get the function in terms of y, like write it as f of y or x equals some function of y, then you can use the shell method. Okay, so this is what you have. You're rotating it about this. You still use dx. That's a special thing. Even though you're rotating it about the y-axis, you use dx. Okay, and everything here is in terms of x. Even the a and b over here, they're also in terms of x. So it's just very nice to use like that. Very convenient. So you put in a 2 pi in front. Okay, the reason for this is too complicated for the scope of this, so I'm not going to go into that, but 2 pi, then a and b, right here, a and b, and then you multiply by the distance from the axis of revolution. Over here, that axis is just going to be a plus whatever this is, right? And over here, they've written that as p of x. So you put that as p of x, and then you multiply that by the height. Okay, and the height is obviously given by h of x, as you can see over there. So you multiply them together and you integrate that. And this is almost always, actually, I'm not going to say that. If you pick it wisely, it can make your work a lot easier. If you pick it when you shouldn't use it, then it can make your work much harder or even impossible. Okay, so use it when it makes sense. Don't have to use this for everything. It's not always going to be easier than the other methods. And it's the same with the horizontal axis, except obviously you change the change all the axes to y's. That's literally all there is. One more thing. So okay, let's just do some practice because there's a lot of stuff over here. Let's begin with this. Okay, there's nothing, there's no practice over there. That's other stuff. Let's go for these questions over here. Okay, these ones. We aren't going to do all. We'll just do maybe one or two. The first one is 2x minus x squared, y equals 0, and you're rotating it about the line x equals 4. So let's quickly graph this stuff out. This is the x-axis, this is y, this is x equals 4. And our function is what? 2x minus x squared. I don't know how to... We can just put in a few points and see what it looks like. So it'll be something like this, I guess. Okay? Just like this. Wait, this seems wrong. Um, 2x minus x squared. Yeah, that's basically 1 plus x minus 1 squared, or 1 minus x minus 1 squared, something like that. Okay, so this shape does make sense there. Thanks, Jigfrig. 0 0 and 2 0. Yeah, I know. Thank you, Jigfrig. So this is 2 comma 0, and then you just continue. 0 0 isn't... Yeah, it is. Never mind. Sorry, I don't know about that. The basically it goes like this. So as Jigfrig there pointed out, and then it'll continue down like this. Now the thing that we want to do is rotate the area between this. Okay, to find the volume of the solid generated by revolving the region bounded by the graphs. Okay, wait, this is a bit complicated actually. We have to find the volume of this, right, between the y-axis and this, rotated about rotated about the x-axis. Sorry, rotated about x equals 4. And this is a practical, pretty useful application of the shell method. Okay, so let's see how we could use that now. Um, okay, let's break this up into two. I think that's the way to do it, right? Because we can basically it's two different things, right? It's this volume when you rotate it about x equals 4, and then this volume when you rotate it about x equals 4. So we'll break it up into two different things. First one will be 2 and pi. Now as Jigfrig pointed out in the chat, this is 2 comma 0, right? Which makes our work easier. It's from 2 to 4. Good work there, Jigfrig. Now the height is basically going to be, think about it, it's 4 minus x, right? So before this they just wrote p of x. Obviously we have to find p of x. It's not that easy either. You have to actually find it, and that's 4 of x. Then obviously the height is just going to be the function 2x minus x squared. I want to save everyone time, so I'm not going to actually integrate it, but you can actually... I will. Okay, it's 8x minus 4x squared minus 2x squared plus x cubed. Might be slightly off. If I make any mistakes, no need to point them out. You can just fix it on your own end because there's a lag between the computer and the thing there. Okay, this is what we have. We integrated from 2 to 4 dx, and then there's a 2 pi in front. I'm just going to do this part. The other one I'm not going to integrate because I have a feeling it'll be a bit messier. So no need to actually integrate that. But this becomes x to the 4th over 4 minus 3x, sorry, minus 2x cubed plus 4x squared from 4 to 2. And then you multiply it by 2 pi. Okay, so it's a bit long here. X to the 4th over 4 will become 64 minus, minus 128 plus, again, plus 64. Unless I'm messing it up somewhere. That seems right. Actually, I don't think this is. Yeah, okay, so that becomes 0. Then I guess you just put in 2, which gives you. So then you do minus. Over here you have 16 over 4, so that's 4 minus 2 to the 4th, which is 16 plus 16. Okay, yeah, this is giving a negative volume, which is something to expect because it's under the y under the x-axis. So that makes perfect sense. Obviously, this cancels out. All of this becomes 0, so we're just left with negative 4 times 2 pi or negative 8 pi. Perfect, right? So it ended up being pretty nice, easy to evaluate. So the volume of this will become negative 8 pi when you rotate it above. But that was the easy part. Now we get to the harder one, which is it's literally the same thing. Literally everything is the same except we just change the bounds here. Okay, so we'll go from 0 to 2, 2 pi over here. And this time we have to do, yeah, 4 minus x is correct. Yeah, so it'll be all the same stuff. Which means, wait, actually, basically it's just the same exact integral, right? So it'll just be this, x to the 4th over 4 minus 2x cubed plus 4x squared. Except you integrate it at from 0 to 2. And then there's a 2 pi in front. Now, we already evaluated this at 2, remember? And that gave us 4, but we subtracted it off. With 0, it's obviously going to stay 0. When you put in 2 again, you're just going to get 4, right? 4 times 2 pi, 8 pi. 8 pi. So it's 8 pi minus 8 pi, which is 0. So when you rotate this about it, it's 8. The volume is 0. If you're taking into account the different signs. If you decide, wait, if you decide not to do that though, then you get, actually I'm a bit worried. I think I messed this up. So let me just check the answer. 1 second. Something is wrong. I'm pretty sure they won't make it like that. You can't have a volume of 0, right? But anyway, 8 pi and negative 8 pi. If you just want to take the positive volume, it'll be 16 pi. If you want to take into account the other stuff, it'll be 0. So let's check the answer now. The moment of truth. So it's a bit before this. It's actually like probably 5, like 4897, somewhere around there. Shell method. There are also applications of the shell method, but we're not going to go into those. Sorry, shell method is one before this. Yeah, right here. So the question is this one, question 23 and 7.3. So 7.3, 23. Let's go to 1250, see if the answer is there. So it's chapter 7, right? So it'll be like pretty far up, maybe 1230. No, 12. Okay, so we're right there now. 7.3, 23, 8 pi. Okay, so uh, we we were right in the middle. It's the average of these two. So must just be some like it's probably just some small mistake in evaluating it, right? Probably something like that. And that's fine. That's fine. But that's basic. Okay, let's do one where I actually get it correct because I don't want to get them all wrong either. Let's do 25. Okay, so let's copy paste the question over here. And this one, wait. Okay. Sorry about that. Also, we need to be a bit more mindful of the space we're taking up because last time I took too much space. Anyway, let's go here. This is the question, right? And let's take a look. This is right after that. I haven't seen the answer, don't worry. Just wanted to make sure. Anyway, now here we're rotating it about x equals 2 again. So when we integrate it, whatever we have, first let's find the points of intersection, right? 3x minus x squared equals x squared. So 3x equals 2x squared, x equals 0, and 3 halves. Yeah, 3 halves and that. Fine. So these are our points. Let me lower the thickness a bit. Let me reduce that. We'll go from, so basically we're integrating, remember, from 0 to 3 halves. You've got a 2 pi in front. Which function is bigger over this interval? Let's just plug in 1 and see. It will be, so if you put in 1, this becomes 2, this becomes 1. So the bigger one is obviously this. So it's 3x minus x squared minus x squared. So it's going to be 3x minus 2x squared. Remember, we also need to multiply by the width or the distance from the axis. The line is x equals 2. So it must be 2 minus x, right? 2 minus x dx. Let's integrate this now. So it's 6x minus 4x squared minus 3x squared plus x cubed. So 6x minus, wait, let's just check that one. 6x plus 2, sorry, my bad. This should be 2x cubed. See, it's, I think I must have made a silly mistake like this in the last question. That's probably why I got it wrong. But yeah, this all seems right. So 7x squared and then plus 2x cubed. So good, we fixed that. You're integrating this from 0 to 3. Let's make some more space here. Let me reduce the thickness again. Actually, we don't even need to write that again. We've got the function there. So it'll be, we can directly take the antiderivative. So that'll be 3x squared minus 7 thirds x cubed plus 1 half x to the fourth from 3 halves to 0. Yeah, this is a bit irritating. And then you put a 2 pi over there. So with 0, luckily it'll all be 0. But so basically we just plug in 3 halves over here, which is a bit messy, but not that messy. We can do it. So let's plug it in. Over here it'll become 27 halves minus um this becomes 27 over 8. Right? Obviously there'll be some cancellations. So this becomes, actually let's put it in directly. 3 halves. Let's just check all the work once. Okay. Yeah, already a mistake here. This should be 27 over 4. This will cancel to give you this, which becomes 27 over 4 minus 63 over 8 plus 1 over 2 times 3 to the fourth, 81 over 16. Let's move it all with a common denominator of 16. Okay, so this becomes, sorry, of 32, because this will become over 32. So to so this becomes plus 81 over 32. This will, let's find this now. This becomes 54 minus 63. Okay, so this becomes negative 9 over 8. Negative 9 over 8. And so you multiply it by 4, you get negative 36 over 32. Okay, this is what we have here. When you add this, when you add them, you get 45 over 32. There's nothing you can simplify there. But you multiply it by 2 pi, right? We can't forget that. So that gives you 45 over 16 pi. Let's just check that. So this is 25. Yeah, okay, this is correct. 45 over 16 pi. So we got that. Let me box the answer here. And yeah, that's it. So, okay, wait, we've already taken 49 minutes and we've only done a few sections. So let's leave that now. Let's continue with these. These are a few questions that I thought are good. Okay, over here, note that there's a pi in front, not a 2 pi. So this is probably, washer or disk method type of thing. And over here, there is a 2 pi. So this is the shell method. You have to explain why they're equal. Over here, we're taking dx. So you're probably rotating it revolving it about the x-axis, because this is washer or disk, right? So washer or disk, this is the shell method. And here it's dy for the same reason. So if we try to graph it out, right? Let's think about it. This, remember, this is r of x squared. So r of x is just x square root of x minus 1, right? Which would look something like this, or well, like this. In other words, we can say that y, this is x, this is y is equal to the square root of x minus 1. If you want to now put it in terms of y, like it's been done, like it's been done over here. Okay, let's also last thing. When we're finishing this off, we've already figured out that this is a washer or disk. Well, not the washer or disk. This is just the disk method. There's no subtraction involved like that. So it's just this. You're going from 1 to 5, right? So this is 1, 1 comma 0, and this is 5 comma 2. Okay, keep that in mind. We've got this. Now over here, where since we're going from with respect to the y-axis, we're going from 0 to 2. That makes sense. 2 pi checks out with the shell method. Because we're rotating it about the y-axis, y makes sense, right? The y, this is the distance from the axis, which is just y at all, sorry, from the axis, which is just y at all times. And then the height, over here, the height is given like this, right? Why is that? Because think about it. The height, first of all, y squared minus 1. Why is it y squared minus 1? Because if you square it, you get y squared equals x minus 1. Y squared minus 1 equal plus 1 equals x. So this is they've made it in terms of x. They made the function x equals y squared plus 1, right? So notice how everything is changing and being flipped into y instead of into x. And the reason it's 5 minus this is because is simple, right? So before, over here we can see that the volume is obviously just going to be this, right? This is what they're going for. Over here though, they're to find the same volume, right? When you're doing it, y squared plus 1 equals x. That's giving you this height, right? You don't want that height. You want this height. So that's why you do 5 minus, right? So that you can do 5 minus this, which will just give you this part. So that's, I know I didn't explain it very well, but that's the intuition. They're just using different representations. And obviously from here, you can also see which one is easier to evaluate, right? One second. This is much, much easier to evaluate because it's just x minus 1. Here you've got a long thing. You've got 2, well, 2 pi doesn't matter, but this is just a bit more complicated. There's going to be a y cubed somewhere in there. There's a lot more stuff here. There's a lot less stuff here. Over here, on the other hand, this will be a bit harder. Over here, it's just x squared over 2, right? The 2 pi, this will cancel out. So you just have the integral from 0 to 4 of x squared dx and then a pi in front. You can evaluate that in your head. It'll be like 81 thirds pi, something like that. Sorry, not 81. 64 thirds pi. Over here, though, you have to figure this out. You have to integrate it, then put in these bounds, and it gets a bit messier. So over here, the shell method, which is this one, is better. Over here, the disk method was better. Okay, so I think that's all we need to know for this one. And this accounted for 2 questions. This will account for 2 questions on my test. So that's fine. Integration by parts. Very, um, this is a formula. I don't really remember the formula. I know how to do it, but I don't know the formula that well. So forgive me if I don't end up using the same words that you might be used to in a calculus class or whatever. Okay, let's just take an example. Let's integrate e to the x times sine of x. Right, this is an easy one. This is a classic one actually. The one that's easier to integrate is obviously e to the, well, not obvious, but it's e to the x, right? Because it's always the same. Whether you differentiate it, integrate it, or do whatever you want, it's always e to the x. So we have this, right? This is our first iteration of the integration by parts thing. And then this becomes e to the x cosine of x dx. Now we do the same thing over here because we haven't simplified this much. We have to do the same thing here. And this becomes e to the x cosine of x again, minus the integral of e to the x times the derivative of cosine of x, which is negative sine of x. So we'll put a sine x dx here, and then the negative we'll put over here. Okay, now pay attention. Now we've got e to the x sine x minus this is equal to this, right? Like these two things. So we'll just plug them in here. We'll pop them in here. Okay. We'll plug that in here, and then this is the special part, right? What is all this equal to? Like what have we been doing the whole time? It's equal to this, right? So integral of e to the x sine x dx is equal to all of this stuff. So it's e to the x sine x minus e to the x cosine x minus e to the x sine x dx. It's still looking very bad, right? Because we have to find the thing. But since they're equal, we can just add this to both sides, and we've suddenly got 2 times the integral of e to the x sine x dx is equal to e to the x times sine x minus cosine x. I think that I might have put a sign error, like plus minus sign error somewhere in here. 2 cancels out when you divide it, and so this is our answer. This is our final answer. It might actually be a plus. I'm not 100% sure. I might have made a silly mistake somewhere in there. Let me just check that. Okay, integral. What is it? Let's see. Uh, Socratic.org. I think it's e to the, yeah, okay. So 1/2 e to the x. So sine x minus cosine x. And obviously there's a plus c. Forgot that. Okay. Just to save time, I'm going to skip the rest of integration by parts because it's pretty much the same stuff. Sometimes you have to integrate or whatever, do the loop iteration more than once. Sometimes you don't. This is trigonometric substitution. You can notice I don't have anything planned out like I did for the other ones here because I kind of forgot about trigonometric substitution. And so we'll all have to do that together now. So it's probably around page 500, maybe 560. Yeah, perfect. Trigonometric substitution. So all we need to know are like the important substitutions here. I think there are two different things here. So there's this one. I'll just copy paste the images here and then put one or two practice questions as well. So there's that one, and then there's another one where you have, some other form. Where is it? Hmm. Um. No, I think that's it then. Okay, let me just check what that picture showed. Yeah, wait. This has everything. Uh, Sine and cosine. You can use sine or cosine for the top one when you're subtracting something, right? And then besides that, you can just do secant or tan. And it does matter which one you choose because they're different formulas. Okay, all of this makes sense just using the, like knowing the different things, tan squared x plus 1 equals secant squared x. Knowing that, it's intuitive, like which substitutions to make where. So I'm just going to go ahead and get some practice questions, like maybe I don't want to make it too hard though, right? Because I'm still trying to hurry up. It's already been 1 hour, and I don't like how slowly this is all going. So I'm going to pick up the pace of it. Right. Okay. And like just wait. Okay, yeah, these become a bit messy, but we'll still do one of them. We'll do number 7. That seems the easiest. Okay, let's copy. I don't want to make it too unnecessarily complicated, right? So, and we also have to do trigonometric integrals, like not substitution, just normal trigonometric integrals. I've got a good idea for one of those. Anyway, let's start with this. The substitution is set to make is 5 secant theta, which we know ourselves because of the formulas up here, right? And it also makes the most sense. Okay, it's the same as any substitution. It's just as they just give it a special name. It's basically a U substitution. So say U equals, sorry, not secant of x. So U equals, and I know they use theta, but I'm just using U. Uh, Hi Adib. So we can just say u is equal to 5 secant x, and then du is therefore, what's the derivative of this? It's 5 secant x tan x, and then obviously there's a dx as well, right, by the chain rule. So we've got du, and we've got that, right? We've got u. So if we wait 1 second, wait, I've done something wrong. Yeah, it's not u equals this. It should be the other way around. It should be x equals that, because you can't really plug it in then, right? You want something for x so that you can directly plug it in. So x is equal to this, which means that this will also get, sorry, this will also get changed up a bit, right? You get, instead of all this, it's kind of the opposite of u substitution, actually. I just realized. Over here, you get dx is equal to 5 secant u tan u du. Okay, so it's kind of the opposite of u substitution. And when you plug this in, you just get the integral 1 over 5 secant square theta, 5 secant theta squared, which is 25 secant square theta, minus 25 will just give you 5 tan theta, tan u. And then we can't put du in just yet. We have to instead multiply by 5 secant of 5 secant u tan u du, because that's dx. Luckily for us, we have a cancellation. So 5 tan u and 5 tan u, which leaves us with literally just secant u du. And it looks very messy, so I'm going to rewrite it once. Secant u du. Um, how do you integrate that? I actually forgot this. So secant of u is just, there has to be a way for it, like a pretty convenient way, but I just forgot what it is. It's like the natural log or something like that. Well, it can't be that difficult, right? Okay, let's see. Okay, we can put in what u actually is, right? That might be easy. U is equal to basically x over 5. So u is equal to x over 5, and then you take the arc secant of that. So it's secant inverse of x over 5. Um, which means that, can you turn on the light, Papa? So it just becomes secant of secant inverse, so it just becomes x over 5. Wait, one second. Okay, never mind. Thank you, Eric. Let's continue then. Wait, this is slightly off. I know there's an easy integral, but I just forgot it. Let's quickly take a sneak peek. Yeah, we aren't expected to know this anyway. I still want to know it, but it's a slightly long one, so no need to memorize it, I think. Natural log of the absolute value of secant x plus tan x. So, natural log of secant u plus tan u. And then the only thing left to do is to plus c, obviously. Right, now we have to figure out, we have to put this back in terms of x, since that's what we were given. To do that, well, what is secant of u? That's just obviously going to be, that's by definition, that's just x over 5. Tan of u, that's where it gets a bit harder, I guess. So let's draw a triangle. This is the main special part of trigonometric substitution. So we know that secant is equal to x, right? Oh, sorry, secant of u, so let's call this u, is equal to x over 5. That means that cosine of u is 5 over x, so this is 5, this is x, and this is therefore x squared minus 25. So what's the tangent of u going to be? It's going to be this thing, x squared minus 25 over 5. And then you take the natural log of this. We can simplify this a bit if we have to, and then plus c at the end. So this should be the answer. I'm just disappointed that I didn't know the secant thing, right? That's something you should know. Um, let's find the, let's check the answer now. So it should be page like 12 for 1230. Let's see. Let's try 8.4 number 7. 8.4 number 7. Natural log of this stuff. Okay, so slightly something's wrong there because we got the same thing, but we divided it by 5 as well. Secant of u is given by x over 5. Yeah, maybe we did something wrong over here. What's the derivative of secant of u? It'll be secant of u tan u du. Over here we got 5 tan x. Seems right. Maybe it's just like whatever. Let's do one more example then. What page is it? It's like, let's see. Okay, right here. We can do one more. We'll take a kind of short one. I don't want to take too long on this. Okay, let's do 20. Okay, this one seems reasonably short and quite easy to do. So let's do this one. But wait, this is 20, right? One sec. Yeah, 20 won't have an answer though because it's an even question. So we just have to check it with Desmos or something. Okay, over here, actually these are the easiest because it's just with sine and cosine, right? So let's say that I'll go with theta this time in case, I don't know. Theta is equal to 2 sine. There's actually probably a way that's better uh, depending on the context, sine or cosine, but I'll just go with sine over here. So theta equals 2 sine x, which means d theta. Sorry, again wrong. Oh wait, that's a problem, right? X is equal to secant. No, never mind. It's not theta is equal to that. It's x is equal to 2 secant. 2 sine of theta. So dx is equal to 2 cosine theta. Wait, this works out like very nicely right now. Sorry, right now it seems. So this becomes 1 over the square root of 2 sine square theta minus 4. Oh, sorry. This is again a secant one. This isn't to be done with sine and cosine. That's if it's 4 minus x squared. My bad. So this will be 2 secant of theta. So dx is again equal to 2 secant theta cosine theta d theta, which means that we get 1 over, yeah, this should be 1 over 2. Again, this should be tan of theta times, wait, this is like almost the same exact thing. It's literally the same thing. So based on whatever their answer was there, since everything else is the same, there should just be x plus the square root of x squared minus 4 plus c. That should be the answer that they have, but it just seems off to me. I'm pretty sure the whole thing should be divided by 2 inside the natural log. The argument should be divided by 2. Let's test it though. So it's 8.425. No, not 25. It's 20. Okay. So we'll just test it then. We'll use Desmos. Actually, with Desmos, we can even check the last question and see. So our answer was the natural log of the absolute value of x plus the square root of x squared minus 25, all divided by 5. So it'll just be minus the natural log of 5. Wait, actually, that might be the thing. You can take that out because that's basically a constant, right? So I think when they put plus c, they might have just factored that in, right? Because natural log of x over 5 plus square root of x squared minus 25 over 5 plus c. Uh, this is equal to the natural log of whatever x plus square root of x squared minus 25 minus natural log of 5, and natural log of 5 is a constant. So just to save that, they just combined that with the constant c and removed it, which actually makes sense. I'm sure that's what they did, because that does make a lot of sense. Similar thing over here, right? So let's graph this. Okay, they want parentheses here, and the function itself is what the oh, we want the derivative of this. Yeah, that's a derivative. um okay, there's something different there. Whatever. So that's f prime of x, and the function that we had was 1 over the square root of x squared minus 25, right? Something like that. Yeah, and they match. They're the same thing. And now if you put a minus or divided by 5, f prime of x, it's the same thing. And now I understand why as well, because over here the denominator never matters. Okay, because even over here you can just write that as like what, minus natural log of, sorry, you can write that as minus natural log of 5, and that's the exact same thing. Same exact thing as this. Yeah, you can see the black line went right over the red line, right? So they're the same thing. That makes sense now. So good, that's gone. And then obviously the second one also must be the same thing. It's the exact same form. Instead of 5 squared, you got 2 squared. So instead of 5 squared here, you'll have 2 squared here. Okay, that's it then. This is a trigonometric substitution, and we're done with that. Let's mark this with a tick. We've taken quite a bit of time on this review session so far, so let's hurry up a bit. This is about an improper integral, from what I can gather from by reading that. Improper integrals, that's section 8.8. Okay, 8.8. So that'll be probably on maybe page 530 or right before that. Oh, no, never mind. Okay, so here it is, improper integrals. There's really nothing special over here. It's like very easy. Only thing might be like, what is an improper integral? I'll just check the definition once, because okay, definition of improper integrals. If f is continuous on the interval negative infinity to b, then um okay, makes sense. Makes sense. No, what is an improper integral though? Okay, here it's written here. In this section, you'll study a procedure for evaluating integrals that do not satisfy these things. Okay, no, so it's basically written up here. The definition, uh, AB. So AB should be finite. If it's not true, then it's improper. And or if it's not continuous over the interval AB, like A to B, then it's improper. So that's a definition thing because there are a few questions on that normally. And then, okay, so all we have to do now is do one or two difficult practice questions and we should be good to go. Okay, 3 to 5. Determine whether the improper integral diverges or converges. Okay, so 40 diverges, right? Oh, well, I should check the odd ones because those are the ones that really matter. 1 over x squared. So the derivative of that will be um, negative 1 over x, negative 2 over x cubed. Negative 2 minus, you can take all that stuff out. Basically, you just plug in 1 over x cubed, right? That's the key part of it. That's the main part. At 1, it's defined. At 0, it goes off to infinity. So the first one is improper. It diverges. Second one will probably, I think the second one isn't even, wait. Oh yeah, at 1 it'll diverge, like completely, but so you have to break that up into two different integrals, from 0 to 1 and then from 1 to 2. Let's try this one. It's got a special color on it, so this might be a good question. 0 to 1 x natural log of x. So 0 to 1 x natural log of x. You have to integrate this. Actually, how do we integrate this? That's the first question. I guess it'll be x natural log of x minus x times x minus the integral of natural log of x dx. So it's basically x. Wait, one second. It should be x minus 1 times x. Wait, this is weird, but I think it's x times x minus 1 times natural log of x minus 1. Something like that. Okay, this is the when you integrate it. And you're going from the bounds 1 and 0. At 0, it's so okay. At 1, it's the whole thing is 0. At 0, the whole thing is 0, which suggests that I've done something wrong over here. Let's just check it once. Give me one sec. X minus 1, natural log of x minus 1. If you take the derivative of this, what do you get? You get that. And if you just do x natural log of x, you get that. So they're obviously not the same. So I've done something wrong. Plus 1. That's wrong as well. Okay, let's just try this again then. Oh, wait, I see. Um, when I integrated the thing, one second. So x natural log of x minus times x. So over here, it's not natural log of x that you put over there, right? Stupid mistake by me. Over here, instead, you put in x natural log of x minus x. Yeah, and that makes sense. And then this is dx. But you can also write this same thing as, let's just rewrite everything. So x natural log of x minus x times x minus the integral of x natural log x dx uh, plus x squared over 2 is equal to the integral of x natural log of x dx. So you get 2 integral of x natural log x dx is equal to whatever stuff is going on here, which is x squared natural log of x minus x squared plus x squared over 2. So that becomes minus x squared over 2. So it becomes x squared natural log of x over 2 minus x squared over 4. And this is what we put in now, 1 and 0. Let's plug this in and see. X squared natural log of x. X squared natural log of x is the first one, and then minus x squared over 4. Okay, again it's wrong. So, oh, never mind. Could be right still. No, okay, both of them are. Wait, what? No wonder. Okay, this is, never mind. Wait, I'm just messing stuff up right now a bit, so bear with me. Okay, that's our integral, and then the thing that we want is x natural log of x. Same thing, right? X natural log of x. Perfect. So we've done it right now, finally. Now all that's left to do is plug this in. So this is our correct integral. When you put in 0, well, 0 doesn't even work, so we can't do that, obviously. At 1, what do we get? This becomes 0, right? Because natural log of 1 is 0, minus 1/4. So it's negative 1/4. Minus, now when you plug in 0, what do you get? So this obviously, the first term will just become 0. Second term also becomes 0. So this seems a bit stupid. It seems wrong, actually. One second. How can this be? Uh, Negative 1/4 minus, yeah, when you put in 0, this becomes 0, this becomes 0. So it's minus 0. So it's just negative 1/4. But that can't be. Okay, let's see. Integral from 0 to 1 of x natural log of x dx. Yeah, perfect. Okay, it is correct, which means obviously it does converge. So we did get that. And actually, this also gave us some integration by parts practice, so that's good. I'm assuming that because it's specially colored, it's a extra good example. I think that's enough. Let's continue from here now. Okay, we're done with this. So, done. Oh, wait, I read, sorry, Eric Johnson, I completely read that wrong. I'm looking at it on my phone, so I thought he said, man, I'm falling for sure. Obviously, you didn't say that, so. Okay, and actually now, good news is we're done with the actual work. Now it's just easy sequence stuff. This one seems like particularly easy. It just says finding the sum of a series, or wait, of a sequence maybe. I'm not sure. My Russian is not that good. Find the sum of a given series. Okay. I don't really know. I forgot the difference between series and sequences. I think a series is the whole thing, right? So, like maybe is this a series? N equals 1 to 100 to 10 of n squared, or n squared plus n. I think it's this sort of stuff. I think that's kind of what the question is, right? Find the sum of a series. Find the sum of a series practice. It might very well just be this, like partial sums and series and stuff on Khan Academy. But just in case it's not that, I should know how to do the other stuff as well, right? Like, what is the summation of x squared? I think that's how you say it, but yeah. I'll just look here. Those are the important ones. There's n, which is n times n plus 1 over 2. Next one is n times n plus 1 times 2n plus 1 over 6. And then k cubed is just the square of k. Okay, so that's another thing to know. These summation formulas, I think that's probably what's going to be asked. I don't know. Anyway, worst case, even if this gets asked, it's only one question out of 10. I'll probably figure something out. Also, the test that I'm taking at least is multiple choice, so that's um, pretty good. Okay, this is basically what it is. So this will be n times n plus 1 times 2n plus 1. By the way, n over here is 10. Okay, I shouldn't write that. Let me change this to k. No, wait, it's all wrong. Uh, so one second. K equals 1 to 10 of k squared plus k. Right? Okay, let's try to do this actually. So it'll be, right now I'm saying n equals 10. Okay, so to simplify it a bit, n times n plus 1 times 2n plus 1 over 6 plus n times n plus 1 over 2. We can factor out an n times n plus 1, and that leaves us with this times 2n plus 1 plus 3 over 6. Right? This cancels out to just give us n plus 2 over 3. Meanwhile, over here we've got n times n plus 1. So it seems nice over here. I don't know. 10, if you plug in 10, over here this becomes 4. Over here this becomes 10. Over here this becomes 11. So it multiplies out to 440. Now let's check that. 1 0 doesn't matter here. It'll be n squared plus n. I think I need brackets. 440. Okay, correct. I think that's, hopefully it'll be something like that, which is, in which case it's easy enough. If not, we'll see later. Question 9. Integral test. I recognize that from here. So this is about the integral test, which means actually there's this one and then there's a limit comparison test. So you need to know both of them, and I think they're both in the same chapter. What a hunch about that. Like probably around here. I think they're in the same section. Maybe the next one. Okay, integral test. So this is that section, at least we can find something from there. Confirm that the integral test can be applied. Okay, what are the rules for the integral test? Like, what are the conditions? That's obviously important to know. So, if f is positive, continuous, and decreasing for x is greater than or equal to 1. So it has to be positive. Obviously, continuous. That's it has to be 2, and it has to be decreasing. So, okay, those are the conditions for the integral test. Then that's easy enough to remember. All that has to be done then is like maybe 1 or 2 questions of practice. So let's find them. Give me 1 second. Okay, let's just take a random one over here. Preferably a slightly harder one actually. Okay, this one is easy, for example. Okay, this one is kind of easy. I'll just screenshot it and take it there. We have to basically integrate it and see if it's like suitable, if the test holds, right? Obviously here, is it decreasing? I guess it is decreasing because n squared plus 1 keeps on increasing, and I'm okay. We need it to be decreasing, right? So we can take the derivative and see that the derivative of arctan of, okay, the bottom will become 1 plus n squared squared. This is to calculate the derivative. We know it has to be continuous because the numerator is continuous, denominator is continuous. So I'm assuming that's true. The first one will become 1 over 1 plus n squared times, okay, this is, I see. So this becomes just 1, and then you subtract it off the other way, which means minus 2n tan inverse of n. It's 1 minus this, so it will be negative. Okay, the derivative is always negative. It's continuous, and it's, well, what's the other condition? I think that's it. Let's just Google it 1 second. Continuous, monotonically decreasing, and the starting value of the series must be lower than the boundary. Fine. Okay, so we integrate it now from 1 to infinity. So this is an improper integral. And the function is just arctan of n, 1 plus n squared. The reason I chose this is because it seems to be a nice integral. If you take u is equal to tan inverse of n, du is equal to 1 over 1 plus n squared dn. Right? So we literally just have the integral of u, so it's u squared over 2, right? And this is kind of what we have. But the bounds change now because we're taking u equals this. The bounds will be, so here we've got n equals this and n equals this. So over here, actually, we'll have u is equal to arctan of infinity. Arctan of infinity is like pi over 2. It goes towards pi over 2, whatever. And then over here we have u is equal to pi over 4. Right? So now this is easy enough to do. You just have pi squared over 8 minus pi squared over 32, which is 3 pi squared over 32. Let's check it once. If now obviously since this converges, then the thing itself converges. Let's test though if this is actually correct. It's basically integral from 1 to infinity of tan, well, I'll just put an arctan, x over x squared, 1 plus x squared dx. Is this the same thing? So 3 times pi squared over, I think it's right. Yeah, 32. Same exact thing. So we did it correctly. That's good. Let's find one more maybe. Okay, this one is again an easy one. Wait, actually it's not. Not too easy. I think we have to use U substitution or something for that. So okay, let's do 16 instead. 16 seems easy. Again, we just use our Desmos to check our work. Okay, got it. This is our question. Let's make some more space for it. This one again, I chose it because it's an easy enough integral. Nice integral. Okay. So we have to just, oh, let's check the stuff now. Like, is everything, what am I saying? Is the derivative, like, is it decreasing? Yes, it is. Um, it is continuous over this range that's given here. And the reason they took n equals 2 instead of n equals 1 is because natural log of 1 is 0. They don't want that in the denominator. So we can just go from 2 to infinity. I think that's how you do it at least. Right? Yeah. Of 1 over n square root of natural log of n dn. Again, a nice u substitution is what you need here. U is equal to natural log of n. Du is equal to 1 over n dn. You've got 1 over n dn, so you've basically just got 2 to infinity. 1 over the square root of u du, which means it's going to be 1 half u to the 1 half. Plugging, now if you plug this stuff in, u is equal to natural log of n. Natural log of infinity will remain infinity. Natural log of 2 will just be natural log of 2, which means this becomes infinite, like it's infinite. So this doesn't work actually. Okay, so let's just test that. And it would, yeah, okay. So it's basically 1 over n natural, 1 over x natural log of x dx. Okay, no, it does converge. So I've done something wrong here. Let me check. I was a bit hasty at the end. Hmm. Wait, what could I have done wrong here? So u equals natural log of n. The du becomes 1 over n dn. So it's 1 over root u. Did I do that part correctly? This part over here. 1 half. Sorry, it's not 1 half. It should be 2. And I think I did a similar mistake in. It should be 2 because, think about it, because when you take the derivative of this, you get that. Yeah, it's 2. That doesn't change anything though. It's basically 2 times the square root of natural log of n. Right? And you're evaluating this from, well, you're evaluating this from infinity to natural log of 2. How can this be defined though? Well, if you plug it in, the square root of the natural log of infinity is not going to be defined. I'm sorry, this is not natural log of 2 then. This is just 2. Right? Because we've substituted back the n. Yeah, something's definitely wrong here. Like this can't be right. Let me check if I put everything in here correctly. Oh yeah, it's square root. Square root. That's a mistake. Okay, now I think it makes sense. Now undefined. Perfect. It diverges. So that's correct. This diverges. With that, I think that's enough to finish this section off as well, because this is already a pretty easy thing, the integral test. It's just the integrals can get hard, but we already covered that. This is the same with the limit comparison test. I kind of forgot the limit comparison test, so we'll take a very quick look at that. If a sub n is greater than 0, b sub n is greater than 0. Okay, makes sense. Makes perfect sense. As long as the limit between them is finite, they either both converge or diverge. So that's good. Let's look at some practice questions here then. These can be done with the direct comparison test, at least this one, 65A. Let's see. Limit comparison test, right? That's what we want to do here. Okay, let's use limit comparison test on this. We can compare it to 1 over n, right? The limit of both of them, limit of 1 over n divided by, wait, which one do you divide by which one? Let's see. 1 second, I should review it once, just very quickly. A sub n over b sub n, yeah, it doesn't matter. It's finite and positive, so it can't be 0 either, which makes sense. And it's a limit as it goes to infinity. Perfect. So yeah, this one over here, natural log of n over n. This should be 1 actually. Natural log of n over n. We can compare it to 1 over n, right? And this is greater than 1 over n. Well, this is the direct comparison test. I should be using the limit comparison test. So let's use that then. Limit as n goes to infinity of 1 over n divided by natural log of n over n. Well, this won't work, will it? This won't work. So we'll have to compare it to something else then. And maybe we can compare it to, well, what do we think? Obviously, we think that this is going to diverge, right? We just need to prove that it diverges. That's all. That's all. And okay, this is done probably best with the direct comparison test, because this is natural log of n over n is greater than 1 over n. This is a p series that diverges, so this also diverges. That's a direct comparison test. What we need to do is the other one, limit comparison test. To do that, we'll do, okay, here, nice practice over here. So let's see, what do they want us to do? This is the same if you use the limits as just 2 to the n over 5 to the n. So that one will obviously converge. This one, you can use a limit comparison test. No, this one again, you can just use the direct comparison test, right? But fine. Sine of 1 over n, that's a, well, okay, let's just focus on the odd ones. Let's not get ahead of ourselves here. 17, 19, 21. Let's just do a few of these, okay? A few of these. There's a lot of freedom with this one, I guess, because it's just like there's so many possible functions you can choose, right? There are infinite functions you can choose. So let's go with the first one. What do we think about it? It seems like it's going to diverge. So we'll try to prove that. We'll do the limit as n goes to infinity of, we can do it with 1 over n, right? So it becomes n over n squared plus 1 times n over 1. 1 over, because we divided by 1 over n. So here we get n squared over n squared plus 1 equals 1. Either they both diverge or converge. The function was 1 over n, that diverges, so this diverges as well. What about this one? Again, say I think we can use the same exact function there, right? So limit as n goes to infinity of 1 over the square root of n squared plus 1 times n over 1 is equal to n over the square root of n squared plus 1. What do they want us to do over here? Yeah, they want us to divide both sides by n, right? So that gives you this. This becomes 1 over uh, the square root of 1 plus 1 over n squared, which becomes 1. Again, this diverges, so this also diverges. Do all of them diverge? Okay, no, not all of them. Not necessarily. Let's take a look at 21 then. This one right here. This one will converge by the same P series test stuff. So we can just say limit as n goes to infinity of 2n squared minus 1 over 3n to the fifth plus 2n plus 1 times. What's an easier version of this? Well, it's just going to be, sorry, what? Yeah, let's show our steps here. We'll divide it by n squared over n to the fifth, or we'll just divide it by n cubed, right? Divided by n cubed. That's perfect. Sorry, divided by 1 over n cubed. What am I doing? Divided by 1 over n cubed. So this is the thing that we're comparing it to. We know by the P series test this converges. So now when we do this, we basically get 2n squared minus 1. Since you're dividing by this, you're basically multiplying it by n cubed over here. Right, you're multiplying it by n cubed. 3n to the fifth plus 2n plus 1. This becomes 2n to the fifth minus n cubed over 3n to the fifth plus 2n plus 1. Again, I think over here they normally want you to divide it by n to the fifth and then show that everything else goes to 0, but this is just 2/3, right? So both of them converge or whatever. Same with the last one, obviously it works. We'll compare it to 1 over n squared. 1 over n times the square root of n squared plus 1. We're dividing it by that, right? We're dividing it by 1 over n squared, meaning by multiplying it by n squared, which gives us n squared over n times the square root of n squared plus 1, which means it's just n over n squared plus 1, square root of that. If you divide it by n and divide this by n squared, since it's under the radical, you again, the same thing as somewhere above here, you get 1 over the square root of 1 plus 1 over n squared. 1 plus n squared goes to 0, so this goes to 1. And since we divided it by 1 over n squared, which converges, this whole thing also converges. Okay, that was fine. Those are much easier than I was hoping, or much easier than I was expecting, so that's perfect. Okay, just a little bit more. Let's see how much time we've taken. So 1 hour, that's all it's saying. Let me check on my end here. Almost 2 hours done so far in this. Um, in this, let's try to finish it within half an hour now. Okay. So this is, so there'll be like 1 to 5 different tests. Okay, there'll be 1 to 5 different tests. Pick one and use it. So there will be 5 different tests. You pick one and use it to prove divergence or convergence. Okay, that's it. Now it's hard to practice it since it's going to be a multiple choice thing. Instead, what I was thinking is we can just take a look at all the tests together and then see right here. Okay, this is list. This is a list of all of them. There'll be 5 of them. Okay, ratio test is an easy one. They converge when the limit of the next term to the first term is less than 1. Otherwise it stays the same. Otherwise it'll diverge, and it's inconclusive and it's 1. Okay, ratio test makes sense. Direct comparison is easy. Limit comparison is easy. Yeah, that's easy as well. Root test, I don't know much about that, so let's see. Limit as n goes to infinity of the nth root of a sub n. You use that when it's like 2 to the n or something, right? Something like that, I guess. So that makes sense. If it's less than 1, basically the same as the ratio test, but instead of taking the ratio of the next term, you just take the nth root. I think it's also called the nth root test. Not sure. Integral test, we know that now. Alternating series, as long as it's decreasing, as the terms are decreasing, and the limit of the final term is 0. I know that. P series, that's the easiest one. Nth term, obviously, we know that one as well, right? Geometric series, that one is also known. Telescoping series, I don't see that's like it's just a very general thing, right? Like you just know if it converges or not. So okay, that's fine. We're ready for this one as well. Nice. Good. Done with this one. Next one, question 12. This is probably the longest I've ever studied for something. It's at least in one go. It's already been almost 2 hours. Okay, this is using a Taylor series centered around C. I forgot, I don't know what the last part is. So, wait, where is the thing? Taylor polynomial to given a rational function. And you just have to list out the first few terms for this. I remember the teacher saying that. Taylor polynomials are right after this, I think. Let's just get some practice. This stuff I do know now because we just did this. Like yesterday we had a test about this, and I got these questions correct. So since it's a Taylor polynomial centered at a value of c particularly, we'll just do one of these. We'll go to maybe 4 terms. So this one seems fine. 28, but we can't check the answer for 28. So let's do 29 instead. Okay, question 29. Root x n equals 2, c equals 4. So it's the square root of n, sorry, square root of x, I think. Square root of x. Perfect. So the first term will be 2. The next derivative will be 1 over 2 root x. Then it will be, okay, let's continue from here. When you plug in 4 over here, you get a derivative of what? Sorry, when you plug in c over here, you got 1/4, right? So you get plus 1/4 x. Then the next derivative, since it's negative 1/2 now, it'll be negative 1/4 x to the 3/2. It's easier to write like this, I feel. Next one will be then, if we just quickly do the math here, 3 over 8 x to the 5/2, etc. I think. Now, so this one is negative 1/4, but remember sorry, it's not x, it's x minus 4. I keep on forgetting that. Now here, the next one will be minus 3, not 3/8, it's minus negative 3/16, x minus 4 squared. And that's all we need because n is 2. But we'll do one more just to, actually no need to do one more. This is enough. We're fine here. Yeah, that seems right. So what question is this? This is question 29 for 9.7. 9.7 is on 668, so I can come back quickly. I'll just write that down. So what is it? It's question 9. 9.7, 29. So let's go to 1250. Let's go over there. 12, maybe 1236. Okay, 9.7 should be right around here. 29. 2 plus 1/4 minus 1 over 64. Okay, that's wrong. Bad, bad job there. Oh, wait, I went one derivative ahead, right? Yeah, wait, I'm actually stupid. This is the third derivative. I went all the way to the fourth derivative, which is wrong. This part is correct. This part, the coefficient is wrong. Obviously, the x minus 4 will be squared only, so that's fine. Coefficient is wrong. So we just plug in 4 over here. That gives us 4. Over here we get 8, so 32, and then you divide by 2, so 64. Divide by 2 because 2 factorial, right? X x minus c to the n over n factorial. Okay, so that's it. That's good practice because all of them are like very similar to this. Centered around C. Only thing to remember when it's centered around C, like do all the work, but then make sure you put the minus C, like x minus C, not just x. Okay. Radius of convergence, not the interval of convergence. It was 668 that we were on. So I'll go over to 678. Radius of convergence is a very easy one here. That's like the one thing that I really remember how to do. But they're not really giving questions about that. Okay, here they are. Radius of convergence. Let's take a quick screenshot and start. Because these ones should be quick, and normally they are quick. I'm going to try like several of these. Okay, so multiple of them. I think I'll do all the odd ones if I'm able to. Okay, this is basically just the ratio test, right? So it's x to the. I'm too zoomed in here. So let's just do the first one over here. One sec. Give me 1 second. Okay, so what do we have? We have x to the n. What's the function? X to the n over n plus 1. So it's x to the n plus 1 over n plus 2 divided by, meaning we multiply it by n plus 1 over x to the n, which becomes x over, and you're taking the limit as n goes to infinity. So you just have x. So that means that the absolute value of x is less than 1, which means the radius of convergence is just 1 over here. So first answer is going to be 1. So let's just write it right here. Second one is, 1 sec. So it'll be 4x to the n plus 1 over, I think this is already just 1/4, but I want to be precise or whatever about it. So you multiply it by n squared over 4x to the n. Cancel with this. Cancel. When you're taking the limit to infinity, these cancel out. So again, this one will be 1/4. I'm pretty sure you can just use the formula for these. Not formula, but basically this part should be less than 1 at all times. I think it's like that. But then there are also radii of convergence that can be like 0 or infinity, right? So let's check this one. Here we have x to the 2 n plus 2 because it's n plus 1, right? So it's 2 times n plus 1 over 2n plus 1 again, 2n plus 2 again, factorial. You're multiplying it by 2n factorial, brackets are necessary there, and x to the 2n. This seems a bit more interesting, right? Now we've got some more stuff to do. We've got x squared divided by, you've got x squared divided by what? Divided by 2n plus 1 and 2n plus 2. Now remember, we're taking the limit. I haven't written this at all. I've done a very bad job with that, but we're taking this limit. So no matter what, these will always go to 0. So here the radius is infinity. This is the radius. Let's check these now. And then the interval, if I get asked that, it's same thing. Right? Just on either side of the C value and then check the endpoints. So 1/4 infinity, 1/4 infinity, the page like 1240 40, I think that's where it is. So 9.8, we want 11, 1/4 infinity, perfect. 679. And this is where we were, right? Okay, let's see if there's anything else about the radius of convergence. Okay, see, this is a bit harder because there are no numbers here, right? You have to do some actual work here as well. So let's try these. Let's try 39. 40 again, it's an even numbered question. They don't give answers to that. So maybe we'll skip that one, but let's definitely try this. Okay, so x minus c to the n plus 1. You're doing the limit, one sec. So it's x minus c to the n minus 1 plus 1. So it's n divided by c. Wait, what is that, c or k or something? I'm not sure. Let me check. Okay, because in they mentioned something about k. So this is c to the n. You're dividing it by x minus c to the n minus 1 over c to the n minus 1. When you do this, you simply get x minus c over c. Right? Okay, now the thing is, over here you want this to be less than or equal to 1. Which means that, um, well, hold up, 1 second. But they said c is positive, right? Okay, if c is greater than 0, then we can just write this as x minus c minus 1. Since c is greater than 0, obviously this is always minus 1. Minus c over c is always negative 1. X over c. We want the, and this is less than or equal to 1, and it's greater than or equal to negative 1. Wait, this, something about this is a bit off, I think. How can that? Oh, okay, makes sense. Sorry. So basically, yeah, 0 is less than or equal to x over c. You're adding 1 to everything, so it's 2. So x is less than or equal to 2c. I don't know if 2c does. Sorry, it's not less than or equal to, it's just less than. So all of these, you remove these lines everywhere. It's just less than, less than. So x is less than 2c, but x is greater than 0, right? It's greater than 0. So the radius here isn't going to be 2c, it's a half of 0 and 2c. That's basically the diameter if you think about it like that. So it should be c. Okay, c for question 39. 12, 40. Okay, so which question was it? Uh, wait, that's, how could I forget that? 1 second, give me 1 second, sorry. This is actually just idiotic. I just said the number and then I forgot it. Let's see. 39. Okay, 12, 40. Question 39. R equals C. Okay. Fine. So that's, I think we're done with radius of convergence. Right, that should be done. Especially because it's not even considering the interval. That's probably not going to make it much harder, but this is very easy. So done with that. This one is about the pros. So question, yeah, next time I'm never writing this in Russian because I just have to look for this for the translation every time. Anyway, so 14 is about partial fractions. Okay, this is where it gets a bit harder. Use a given power series to find another power series centered around a specific C value. I haven't really done that. Like, I don't know what they mean by that. I should see an example of that. Right? So, let me do that then. Let me look in the book. If I can't find it in the book, I can Google one. I just need like one example because I can do it when it's not asking for um a particular C value, but whatever. Okay, let's Let's just quickly go over 9.9, representation of functions by power series. But maybe they just mean, first of all, this first part is like not relevant. That was just something specific. It's only apropos to our class. Use a given power series to find another power series. Maybe they mean that this is, maybe they're counting this as a power series. It is, right? It's just like summation of a r's a r to the n. Yeah, that's what it is. I think that's what it means. In which case, I'm skipping it because that's like quite easy, and I just took the test. Like I took the test yesterday. I got all that stuff correct. I got a 98 because I messed up one of the things. But the point is that all these recent concepts that we were touched on, I understood those well enough, obviously. So I'm not going to worry about them too much right now. Use the definition to find the Taylor series centered at C something. C equals something for a given function. We'll use summation or sigma notation. Now, obviously, sigma notation is something I'm pretty used to. Um, Form of a convergent power series. So there's something here. Definition of Taylor and Maclaurin series. It's equal to this. I think the point is that you should be able to find some shortcut or whatever. Basic. What I mean by that is it's kind of like. Wait 1 second. Let me try to remember the question. There was a question about this just a few days. I just had the question. Give me a minute. Let me get the. Uh, I'll just go and get the what's it called? I'll get my test from yesterday and just see over there. Okay, so I'm back now. I got my test as well. So the question is, 1 sec. So let's go back there. The question was, using the binomial series theorem, find the power series for f of x equals the square root of 1 plus 2x. Right, that's the question. So basically, since the formula is the formula for 1 plus x to the k is but actually this is just a binomial theorem, right? It's uh, wait 1 second. This is just equal to, oh yeah, this is equal to n equals 0 to infinity of k choose n x to the n, right? This is basically what it is. Actually, I think that's literally just a binomial theorem, right? And then if this was like p or something, then this would be p to the k minus n, or whatever, something like that. Okay, so okay, this is good. This makes sense. The thing is though, if k is not an integer, then it becomes a bit, you can't just write it like this, right? So you have to write it a bit differently. Over here, x becomes 2x, and this becomes 1/2. So it's like k equals 1/2 and x goes to 2x. And so this, if you look at the first few values, it'll be like k, just k, then it becomes plus, wait, 1 second. If you put in 0, then this becomes just 1, because k choose 0 is 1. Plus, then if you put in 1, you get kx, then you get k times k minus 1. And what does this become? This becomes, so you put in 2 over here, right? So this becomes, yeah, over 2 factorial x squared plus k times k minus 1 k minus 2 over 3 factorial. I think it goes on like that. I think that makes sense. Yeah, x cubed and so on, right? And so on. So, that's how you write it. Now when k is half, it becomes a bit interesting. And remember, x is also 2. So this becomes 1 plus kx becomes 1/2 times 2x plus 1/2 times times 1/2 minus 1. So that becomes negative 1/4. When you divide it by 2, that becomes negative 1/8. So this is obviously a minus. But then it's 2x. Remember, it's 2x, not x. So it becomes negative 1/8. So minus 1/8 times 2x squared. So that becomes 4x squared. So this becomes minus 1/2 x squared. Okay, then the next one becomes plus. Instead of minus 1/4, which we had here, it becomes negative 1/4 times negative 3/2, which becomes 3/8. Then you're dividing it by this. But at the same time, you're multiplying it by 2 cubed. So this cancels with that. And you've just got 3 over 3 factorial, which is again a 2. So this also becomes 1/2 x cubed. Then you have minus, and so on, right? But the thing is, we have to like put this into one summation. The way to do that is to write it as like what it is, right? So this becomes, instead of simplifying it, we're not supposed to simplify it. I think that's incorrect. This becomes 1/2 times negative 1/2 times negative 3/2 times negative 5/2 and so on. I'm not talking about this term anymore. I'm just talking about in general. This becomes a numerator, right? And then this becomes like some n factorial. And this obviously becomes x, but not x. It's 2x to the n, right? This is basically the general form that we have. 1 second. I think I'm onto something here, so I'll just remove all this stuff. Right, this is basically what you have for each successive term. We leave the first two, 1 and then 1 plus x, right? It became 1 plus x plus. We'll continue from there because that's when we really start to see the pattern. So we've got this. Now, how many terms are there? Remember, there's a half, 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 half coming from each of these. So we can take that all out to the bottom. The 1/2, like the 1 over there doesn't matter. We can remove that. So now we've got negative, 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 right? How can we now express like this product in terms of n? Okay, so over here when we got 2, when we had 3, it became 3. When we had 4, it became 5, right? So the formula, if you continue like that, it becomes 2n minus 3. So this is 2n, so it's basically 2n minus 3, 2n minus 3, and so on. The number of terms that come up here are always enough, like exactly enough. See that two, there's 1/2, negative 1/2. So there are two twos in the denominator, right? Those will cancel out with the two x's, two twos over there. So those cancel out. So all these, this denominator cancels out with the 2 here completely. Okay, completely cancels out. So then all we've got left is basically negative 1 to the n. Sorry, not negative 1, negative 1 to the n or n plus 1. Not sure yet. We'll just check that later. And then this product over here becomes 1 times 3. I'll write it like this: 1, 3, 5, and so on until 2n minus 3. Right? And then obviously right at the end, you've got x to the n. This is what we have. Now we need to just check it with 1 or 2 terms and make sure that it's all making sense. if you put in n equals 2, then this part works out, this part works out. With n equals 2, we had 1/2, -1/2 x squared, right? We had that. So the negative is there, which means that this is an odd number. So we just make this n plus 1. Okay, right here, it'll be n plus 1. So that the signs match. Now our final answer here is -1 to the n plus 1. Over here you've got 1, 3. You can write this as a product, okay? We didn't do that in the test because we didn't have to. Like I think she said the teacher said not to do that, so we didn't do it. But over here, like I guess you could write this as a product from k equals 2 until n of just 2k minus 3, right? You could write it like that. And then this becomes x to the n. And then this is all obviously in a sum itself. N equals 0 to n. No, not 0 though. Okay, because we've already done the first two terms. So this is n equals 2 until infinity. N equals 2 until infinity. And then in the front we've got 1 plus x. I think we could still do the same thing with the first two terms. So with like n equals 1 and 0, but then this product over here would get messed up, right? And we don't want to do that. So basically this is our final answer. I'll write it down once more just to show how it looks. And this is basically what the question was. I think this is literally what the question was. Yeah. I didn't include the product in the answer obviously because she said not to do that, I think. But this is one way to write it. So this is the answer here, right? Oh wait, the point is that this should be centered. So I think this is what the definition is, right? That it'll look something like this. There'll be this over here, there'll be this, and then this becomes a derivative. This becomes a derivative, something like that. I don't know. The only thing different here will be that instead of like when we get these derivatives, we'll have to. Sorry, wait. I don't know why I showed this. This has nothing to do with. This is using the binomial series theorem or whatever. Instead, we'd have to, like here the x to the n would go to x minus c to the n, right? And then we'd use the derivatives. And then similar to how we developed this formula over here, we'll have to develop a formula for that. There was another example of that somewhere, but I don't know. I think it's somewhere else. I don't have it with me right now. So that's it. Um. Anyway, with this, we've now done 14 and 15 as well, right? We've maybe not in much detail, but 14 and 15 are done. Oh, the things went. Okay. So and now it's 6 o'clock for me. So 5:59. So I think that's more than enough of all of this stuff. It's been 2 hours and 15 minutes, which is most likely my longest stream ever. So I'll leave it at that. Thank you for watching, and I'll see you. I'll see you all some other time. That's it. Bye.